Hello friends and my dear students, I welcome you all to my channel. I hope you are all well and your studies are also going on well. This is part 9 video on the subtopic of thrust and pressure from the chapter of force and pressure, where I will discuss about the pressure exerted by different solid structures and the pressure exerted by liquid columns. So this video is part of the playlist ICSE Physics for Class 8, where I primarily discuss about key concepts and formula related to numerical problem solving. If you find this video beneficial, then please like it, share it with your friends, and if you want to further support me, then subscribe to my channel, and in that case do not forget to press the bell icon so that you will be notified by my future videos. So let's start part 9 video, where I will discuss about pressure exerted by solid structures and liquid columns. Okay, how do we actually find the pressure exerted by a solid body that is having a mass and that can rest on a surface, that can rest on one of its sides on a flat surface? So take for example this figure. This is example 1, where I have this is a solid structure. In the figure A, you can see the structure is having a total mass of m kilogram, and it is resting on a surface which is having the side of the body structure which is resting on the surface, solid surface. Its area is x meter square. In the second figure, it is the mass of the structure is same, that is m kilogram, but it is resting on the surface, on a contact area, on a contact surface, which on two legs. The first one is having one leg, the second one is having, consider this to be a table or chair or tool. So the second figure is having two legs, where each of the legs is having a cross sectional area or the area of contact of each leg with the ground or floor is x meter square. In the second, effectively in figure B, the total area of contact is x plus x, that is 2x meter square. In the figure C, we are having the same structure is having three legs, where the area of contact of each leg is x meter square. So the effective area of contact of the entire body or structure with the ground or floor is 3x meter square, and the mass is same, m kilogram. So as you can see, it says that pressure exerted by solid structures, pressure is weight of the body, that the weight of the body will always, if the structure is standing upright, and it is not standing in a inclined direction, it is standing vertically, then always the weight of the body or structure will act vertically or normally to the ground or floor. Okay, so weight of the body divided by net area of contact. So if I try to find the pressure exerted by the structures, I will have for figure A, the pressure will be the force or the thrust that is acting on the ground is definitely coming from the weight of the body, which will be x kgf, divided by the area of contact, which is x. So this is equal to, this is m kilogram, m kgf. So this is m by x, this is x meter square, you can say, and m kgf is equal to, I'm not converting it to a Pascal, I'm just leaving it this way only. So this is m by x kgf per meter square will be the pressure that this structure in figure A is exerting on the ground. For the figure B, pressure will be the total thrust, which is the weight of the structure, which will be m kgf divided by the net area of contact, which will be x plus x, that is 2x meter square. So this is equal to m by 2x kgf per meter square. Now this m by x and m by 2x, these are not any formula that I am trying to discuss. I am just trying to discuss what happens, what will be the pressure, how to know the total thrust acting on the ground by the body, and how to compute the net area of contact of the body or structure with the ground or floor. Okay, so the third case, in the figure C, we can see the pressure is same, the thrust or total vertical force, it will be the weight m kgf. This time the net area is 3x meter square. So this becomes m by 3x kgf per meter square. So this was just an illustration to let you know how you will find the net area of contact of a body with any surface. So for the figure A, as you can see in the formula says pressure is equal to weight of the body divided by net area of contact. So for figure A, this capital A is x meter square. For the figure B, the capital A is 2x meter square. And for the figure C, the capital A is 3x meter square. So that was one example. Let's see another example. The second example is a cuboid. It's a solid cuboid which is having a height of h meter, length of L meter, and width or breadth of B meter, where obviously we have the height is less than the breadth and the breadth is less than the length. Now if this cuboid rests on the ground on its different sides, what will be the pressure? So in the figure 1, the cuboid, the solid cuboid, is resting on the side whose area is determined by the height and the breadth, that is B and H. It is resting on this side or this side. So the area for the figure 1, in the situation 1 or figure 1, the area of contact will be B into H meter square. And in the in the second figure, the same solid structure cuboid is resting on a side whose area is determined by the length and the height. So it is resting on this side or this side. So for situation 2, figure 2, the area of contact will be LH meter square. In the third situation, third figure, the solid cuboid is resting on the side whose area is determined by the length and breadth, that is this side or the bottom side. So definitely the area of contact will be B into L, length into breadth meter square. Now this entire solid structure, the mass of the entire solid structure is m kilogram. So definitely in all the three cases, the weight, the thrust will be same, that is m kgf. Let's see what will be the pressure. The thrust is m kgf. Since the mass we are considering to be in m kilogram, divided by the area of contact is bh meter square. Okay, so this becomes m by bh kgf per meter square. Okay, for the situation 2, the pressure will be equal to the total thrust, that is the weight, which is m kgf, and the area of contact is LH meter square. So this becomes m by LH divided by m by LH, this much kgf per meter square. And for the third scenario, the pressure will be the thrust, which is mkgf divided by the area is lb meter square. So this is m by lb, this much kgf per meter square. Now if I want to determine which pressure is the largest, in which position this solid cuboid is exerting the maximum pressure on the ground. Obviously the pressure will be, since the thrust m kgf is constant, definitely the pressure will be maximum when the area of contact is minimum. Now in all these three situations, if you consider the area of contact, if I want to compare them, clearly I will have BH will be less than LH, and LH, this will be less than LB. Since we know that H is less than B is less than L, then we must have BH less than LH and less than LB. Now we can clearly say, let's consider the pressure 1 in figure 1 to be P1, this is P2 and this is P3. Since BH is the minimum and LB is the maximum, we can clearly say that P1 will be the maximum. So P1 greater than P2 greater than P3. So in the position 1, the pressure exerted is maximum, and in position 3 the pressure exerted is minimum. Okay, let's see another example. In this example, as you can see, the area I am shading is an iron nail, which we are trying to hammer it on a wall. So this is an iron nail. Clearly the area, which is clearly the pointed area. So this iron nail is held vertically on a wall. This is the wall is held vertically, and the pointed part of the nail is having a cross-sectional area of smaller meter square, and the head of the nail is having the area as capital A meter square, where obviously we know that the small a is always very, very small compared to capital A. This is a mathematical notation where it's means that the magnitude of A or the value of A is small, very small compared to capital A. Now let's say I am applying a force F. This force F is being applied parallel to the nail on the head, and of course this force will be vertical or perpendicular to the surface of the ball. So now if I ask what will be the pressure being applied on the head and what is the pressure being applied on the pointed area, now what is the pressure applied, now what is so the question is, what is the, if I am giving a force, if I am hammering this nail with a force F acting perpendicular, acting parallel to the nail, which means perpendicular to the surface of the ball, then what is the pressure being applied on the head and what is the pressure being applied by the pointed part on the surface of the ball. The important thing to note or understand is that whatever force I am applying, this force F will also be applied over here by the pointed part on the ball surface, on the surface of the ball. So this is also F. So clearly the pressure P, if I consider P head to be the pressure being applied on the head, this will be the net thrust or force, which is F, divided by the area of the head, which is A. This much, let's say the force being applied is Newton, F Newton, F Newton. So this is F by A Newton per meter square. This is the pressure being applied on the head. Okay. And if I consider the pressure being applied on the other end, that is pointed end, what is that pointed end called? I don't know. Let's say pointed. P pointed means the other end of the end of the nail opposite to the head. So this will be F by small a Newton per meter square. Now since the same force thrust is being applied, I can say that I can have a relation or result that capital A into P head will be equal to small a P pointed. That is, the area, since the force is same, since the force, even though I am hammering on the head, that force with which I am hammering the head, which is F, that force will also act on the pointed part. That is, that the pointed part will also give a vertical force of F on the surface of the wall. So I am having A, capital A into P head is nothing but the force F, which is equal to small a into multiplied by the pressure applied on the surface of the wall by the pointed part. So this is, we will have this relation. Okay, so this was, I think, some standard results of how pressure is being created by some solid structures when they are resting on a flat surface. Let's see, now let's discuss what pressure is exerted by liquid columns. So just like solid, liquid also exert pressure on the container. So in the figure 1, we are having a container which is filled with the liquid having density rho. Let's say it is rho kilogram per meter square is the density of the liquid, and the height of the liquid, the level of the liquid is h1 meter in the first figure, and the cross-sectional area of the container or the area of the base or the bottom is a1 meter square. In the second figure, we are having a different container. The liquid is same, but we are having a different container where the cross-sectional area or the area of the bottom is a2 meter square, where a2 is less than a1. a2 is less than a1, and the height of the liquid in the container is h2 meter. Also h2 is less than h1. In the third figure, we are having another different container where the cross-sectional area or the area of the bottom is a3 meter square. a3 is less than a2, and the height of the liquid or the level of the liquid is h3, where h3 is also less than h2. The fact is that the pressure exerted by the liquid in all this scenario, the pressure exerted by a liquid on the bottom surface of the container only depends on the density of the liquid and the height of the liquid. This is the fact, and let's see if this is true or not, whether we can derive this fact or not. Now, quite obviously, in all these scenarios, if I try to find the pressure exerted by the liquid on the bottom surface of the container, the total thrust acting will be the weight of the liquid. So in the first case, if W1 is the weight of the liquid, it will be the volume. The volume of the liquid is the cross-sectional area of the container or the area of the bottom surface, which is A1, multiplied by the height of the liquid, which is H1. This is so this is the this much meter cube is the volume of the liquid. I am sorry, the density of the liquid will be rho kilogram per meter cube, not square. I'm sorry, per meter cube. Okay, so the mass of the liquid in figure 1 will be its volume, which is A1H1 into density. This much kilogram, which is equal to A1 H1 rho, this much kilogram. Okay, let's see what actually kgf, since it is weight, the weight will be kgf. For the figure 2, what will be the weight of the liquid column? The volume of the liquid column, which will be A2 H2, and the density, this much kgf. Okay, for the figure 3, the weight of the liquid column will be A3 H3 rho kgf. Okay, so this is the total weight of the liquid column, or the thrust being applied by the liquid column on the bottom surface of the container. Now let's see what will be the pressure. For the figure 1, the pressure P1 will be the thrust, that is the W1 divided by the area of the bottom surface of the container, which is A1. This becomes A1 H1 rho divided by A1, this much kgf per meter square, and this is equal to A1 cancels out, we have H1 rho, this much kgf per meter square. See, in this expression we are not having the cross sectional area of the bottom surface of the container. So, and the only factor we are having is rho, that is the density of the liquid, and H1, which is the height of the liquid column. Similarly, we will have pressure exerted in case of figure 2 will be W2 divided by A2, which is again will be A2 H2 rho divided by A2, which is equal to H2 rho divided by H2 rho kgf per meter square. Quite obviously, we will also have for figure 3, P3 will be equal to H3 rho, this much kgf per meter square. So clearly we see that if we have a liquid column on a container, then what will be the pressure exerted by the liquid column on the container, that is the bottom surface of the container, it will be the density, it will be the height of the liquid column, and the density will depend on the height of the liquid column and the density of the liquid. Now if you ask what exactly will be the, now you must understand that kgf is a relative unit. If you want to know what will be the exact pressure, then I have to convert the kgf to Newton. So this will be equal to, if I consider G to be 10 meter per second square, then this pressure will be 10 H1 rho, this much Newton per meter square, or this will be 10 H1 rho Pascal. Similarly, we will have for P2, it will be 10 H2 rho, this much Pascal, and P3 will be 10 H3 rho, this much Pascal. So we clearly see that the pressure exerted by a liquid column of height, where the height of the liquid column is whatever, if is H and the rho is density, then the pressure is 10 into H into rho Pascal, if we consider the value of G, that is the acceleration due to gravity on the earth surface, to be 10 meter per second square. If you consider 9.8, then it will be, in all the cases, the pressure will be 9.8 H rho Pascal. Now one important thing to understand is that, so this was the pressure exerted by the liquid column on the bottom surface of the container. Now the liquid, it is a fact that the pressure exerted by liquid is the same in all direction. What does it mean? If you consider the pressure exerted at the bottom surface of the container, then the pressure, let's say this pressure will be same. This is whatever the pressure is for figure 1, which is 10 H1 rho. This pressure will also act this way, sideways, on the left hand side, horizontally to the left hand side, and also horizontally to the right hand side. The same pressure will act. On the sides of the container at the same level, that is at the same height, H1. So let's try to understand this. Let's say we are having a liquid. It is filled with liquid with some density. Now obviously the pressure exerted, let's say the pressure if you consider any point on this liquid, which if you consider all the points, if you consider all the points in this liquid which is at the same height from the surface of the liquid, let's say if you consider this is a point A, and let's say the point B is also at the same height as point A. Let's say this is another point C which is at a greater height than points A and B. Okay, let's say so the pressure exerted vertically down at the point A, let's say this B, even though this symbol is for force, let's say this be pressure PA vertically down. The same pressure PA will act sideways. This will be PA. Let's say at the point B, the pressure acting vertically down is PB, and this the same force, the same pressure PA will act sideways. So, and let's say the pressure at the point C that is exerted by the liquid on the side walls of the container, let's say this is PC. Now essentially now if we want to compare the pressure at the point A either vertically down or on the side walls of the container and the pressure at the point C and B, clearly we will have PA will be equal to PB, because the point A and B are at same height from the top surface of the liquid. If this is H, the point B is also at a height H, and let's say the point C is at a height twice H. So clearly we must have PC greater than PA. The pressure exerted at the point C by the liquid, either vertically downwards or laterally sideways, that is to the pressure acting on the side walls of the container, it will be the same. So at a particular height, the pressure of the liquid will be same in all directions. In all directions it will be same. So if you consider that is let's say we are having a container liquid, the pressure of this liquid exerted, the pressure exerted by this liquid on the bottom surface of the container will be same. So vertically down it will be same. All this pressure, it will also be same on the side walls. They will be same. So this was all about the pressure exerted by different solid structures based on their weight and the net area of contact with the floor or ground, and the pressure exerted by a column of liquid of a certain height and the density. The cross-sectional area of the container where the liquid is filled, that does not matter in finding the pressure of the liquid at any particular point in the container. It all depends on the height of the point from the top surface of the liquid and the density of the liquid, and also of course on the G value of G, because if you measure the pressure, let's say, quite obviously, let's say this is the R. On the surface of the R, you are measuring the pressure of, let's say, this is a container. This is a container with some liquid having density rho, and the height of the liquid column is H and density rho. Then definitely the pressure exerted on the bottom surface of the container will be actually it will be H, rho and G. This G is the acceleration due to gravity on the surface of Earth, whose value we know is 10 meter per second square or 9.8 meter per second square. This much we can say, if we consider height H to be H in meter and rho to be in kilogram, so H meter, let's say H meter, rho kilogram per density of the liquid is rho kilogram per meter cube. Then the pressure exerted by the liquid on the bottom surface of the container, where this container is on the surface of the Earth, will be H rho G, this much Newton per meter square, that is H rho G, this much Pascal, where we know that the value of G will be 10 meter per second square. What if we take the same container at a height, at a very high altitude? At a very high altitude, the same container, same liquid and the same height H meter, the same liquid, that is density is same, rho kilogram per meter cube. What will be now the pressure? What will be now the pressure? This time the pressure will be, H is same, rho is same, but the acceleration due to gravity will be different. This much Newton per meter square, or H rho G dash Pascal, where definitely G dash will be less than G, because we know the acceleration due to gravity decreases as we go higher up in the altitude, higher up from the surface of the Earth. So G dash will be less than G. So quite obviously the pressure exerted by the same liquid of the same height will be less. Okay, so this was all about the pressure exerted by different solid structures and the liquid columns, and how do we actually compute them. Based on these concepts, I will solve a few problems in the next video, that is part 10. So please stay tuned for that. If this video was beneficial, then please like it, share it with your friends, and once again please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. I will end the video here. Thanks for watching, and until the next video, take care and bye.